and the forward path transfer function of for a negative feedback control system that is given as G of S equals K S by S plus 1. And the feedback path transfer function that is given as H of S, and it is equal to 5. Now what we have to do here is we have to find out the sensitivity of the closed loop transfer function. Okay. Sensitivity of closed loop transfer function with respect to G and H both at omega is equal to 1 radian per second. We have to assume the value of K here as assume K equals 10. Okay. So you know that when we have a closed loop transfer function, how do we define the sensitivity of that? Yes. What will
Yes,
be
ma'am.
this? Yes. Okay. So what will be the sensitivity of the closed loop transfer function if we see? Sensitivity that is given as, yes, anyone? With respect to G, if we see, then it is given as 1 by 1 plus GH, right? Do you agree with this?
Ma'am, here GH is it equal to GS into GC?
GS into?
No.
No, see, this is
Oh,
our
okay.
forward path GS, right? As per the usual notations which we follow, correct? This is our RS. This is our CS, right? And this is our HS. These are the usual notations which we take, okay? And this is our negative feedback control system, correct? Okay. The value of
Yes,
HS
ma'am.
is given as 5 and this is K S plus 1. Okay. So if we now have to find out the sensitivity of this closed loop transfer function, it is given by this expression, right? And we can
Can
now,
we drive it first?
yeah, definitely we can derive it also. Have you gone
That
through
will be
this?
helpful.
Yeah, we can do that, no problem.
Yeah, I've gone through the video lecture, but this part, like sensitivity part, was a bit unclear to me.
Okay, no problem. Others also, we need to derive that. Okay, we'll do that, no problem. We'll do it quickly. Okay. So
Sure.
you know that if we have a closed loop configuration as which we have drawn here, and if there is a say small change in GS, that we can write down as GS changes to GS plus del GS, right? And it may be due to a parameter variation, and correspondingly we have change in output CS, right? And that is the CS changes to CS plus del CS, right? Correct. Now what generally is our assumption while deriving this expression is that we assume that the magnitude of this GS is very much greater than the magnitude of this small change, which is due to some parameter variation in the system, right? Now, if we now use this expression, that is relating the input and the output of this feedback system, what we will get? We'll get here, we know that we can write here as the CS is equal to GS divided by 1 plus GS HS into RS, right? Or CS by RS is equal to GS by 1 plus GS HS, correct? Is it okay?
Yes, ma'am.
Now,
Yeah.
due to this del GS, how this is going to change, and this, let us see that. Okay, so we can write here CS plus del CS, that is equal to GS RS 1 plus GS HS plus del GS RS divided by 1 plus GS HS. I've written it in a single step and I've like expanded it because GS becomes GS plus del GS. Correct? Is it clear? Right? Yes? Now if I write here,
Yes, ma'am.
okay, if I write here this as
One clarification.
Yes,
When GS is changed to GS plus del S, del GS,
right, right.
that will also impact the denominator, right?
That will also
Impact the denominator. In denominator, we have 1 plus GSHS, right?
okay. We will ignore the small change of. That's why we have taken this
Okay.
assumption. Okay.
That's why we. Okay,
Yeah,
fine,
we
got
are
it.
ignoring the change in del GS in the denominator. So our equation is taking this form, right? In order to simplify,
Okay.
because it is very small.
Okay.
Okay. Now, if we
Okay.
compare both the sides, can I write down here that del of CS is equal to del GS RS divided by 1 plus GSHS? Now see, because it is in the denominator, na, even if we are taking into consideration 1 by like if we are adding 1 by 3, and if 1 by 3 plus 0.00, it will be even a smaller value, right? So that's why we can neglect
Yeah.
it here. Okay, so here if we see the change in the output due to this change in our gain, we'll get this. Okay, so now recalling this, the transfer function which we have written here, and this is what we have obtained here. If I want to find out the sensitivity of this transfer function, okay, with variation in G, fine. Now what I'll do, I'll calculate the sensitivity of our transfer function to variation. Okay, first of all, let us see how we'll designate it. That, you know, I'll write it as SG, and this is subscript and this is superscript. Okay, and how can I express this? This is equal to percentage change in transfer function, right? We've seen here that how our this transfer function changes. Okay, here we can see how it changes by percentage change in G. Is it okay? Gaurav,
Yeah.
is it correct?
Okay.
Now, if
Yep.
I want to write this percentage change in transfer function, I'll write it as del t by t divided by del g del g by g. Okay, so this can be written as del t by del g into g by t. Okay, please mute your mic, all of you.
Sure. Yeah.
So I can now write down this del t by del g as what? See here, because what is my transfer function? I'm just like no taking only a t and g, and it is understood that we are talking of S domain. Okay, here we are just omitting the variable s for ease. Okay, don't get confused. Fine. So I can write down this del t by del g as 1 plus gh minus gh by 1 plus gh whole square. From where does it comes? Yes, we have t as c by r, that is t of s cs by rs, that is equal to g by gs of 1 plus gh. Now I'm differentiating it with respect to g. So this is a numerator. You apply that derivative rule. What it is? Denominator, okay, into derivative of numerator, that is del by del g of g,
Yeah.
1.
Got it, ma'am.
Yes, that is how, and divided by the square of the
You are not
denominator.
audible, ma'am. If you are speaking,
Yes,
am I audible?
yes, yes, you are audible. Could you hear me? Hello.
Yeah, yes, ma'am. You are
Yes,
audible.
ma'am.
Okay.
Yeah, you are audible, ma'am. Thank you.
Okay, okay, okay. So what will get here? Tell me. 1 by 1 plus gh square, right? Is it clear? This is del
Yeah.
t by del g. That is what I have written. Okay, del t by del g.
Yeah.
Fine. Now
Yeah.
coming back to this, what it will be? 1 by 1 plus gh square into g divided by t. And what is t? T is again g by 1 plus gh. So how much it is going
Yeah.
to be now? This comes out to be,
Yeah. So 1 plus 1 by, oh, sorry, 1
yes,
divided by
1
1
by,
plus gh.
yes, got it?
Yeah. Thank you, ma'am.
Similarly, you can find it out for the closed loop also, starting from the beginning like this. Okay, for open loop system also you can find it like this. So if I can,
This one that we have done is for closed loop, right?
correct, right, okay,
Okay.
fine. And similarly, as we have found the sensitivity of the transfer function to the variation in g, we can similarly find out the sensitivity of the transfer function to variation in h also, right? That also I can evaluate
Okay.
for h. Fine. So we have to do in the second part for h also. Okay, for the question which will be looking at. Okay, so coming back to our question, let us see what we'll be doing here. So our GS is again this much, HS is this much. So let us use this expression which we have derived just now, and putting the values, what we'll get, sensitivity with respect to G, that is 1 by 1 plus, and G is how much? G is 5 by S plus 1, and okay, into K. HS is this into K, right? And solving this, what we'll get? s into s plus 1 divided by s square plus s plus 5k, right? Now we have to find out the sensitivity at omega is equal to 1 radians per second, and we have been given that assume the value of k equals 10. Okay, so let us see on putting s as j omega what we'll get. Okay, so this is, you can write down this as, here this can be written as s square plus s divided by s square plus s plus 5k. So if I substitute now here j omega, let us see what our expression will be. Correct? This gives us j square is minus 1. So minus omega square plus j omega divided by minus omega square plus j omega plus 5k. Right? Now taking the magnitude to calculate the value, of course at j omega, and putting the value of k as 10, what it will be? Let us see. This is this can be written as, since this is a complex quantity, can I write it as omega square square plus omega square, and arranging the real and imaginary terms, what I'll get? Here I'll get 5 into k, that will give me 50, right? 50 minus omega square square plus omega square, right? Is it correct, everyone? Is it clear?
Yes, ma'am.
All of you?
We are trying to find the absolute value of sensitivity here, right?
Correct, correct. We have to find out the numerical value, right? So we have done this, and now it is for you to calculate and tell me the values at omega is equal to 1. Substitute the value of omega as 1 and solve it. What you'll get? How much is the answer?
Uh, 0.2.
0.2
2.
or 0.02? Just solve it properly.
Yeah, 0.02885549.
Correct, correct, correct. Perfectly correct. 0.02885. All of you getting it? Please tell.
So, ma'am, one doubt
Yes.
that might be slightly off the topic, but while calculating absolute value, we have not divided our expression into real part and imaginary part
No,
directly.
we have done
Means-
that. See, in the numerator we have this of the form a plus ib, right? You can see here.
Yeah,
Okay, and
yeah,
in the
A and
denominator
B,
we
yeah.
have, yeah, in the denominator we have 5k minus omega square plus j omega, right? So if
Yeah,
I'm finding out the magnitude of this complex quantity, it is a square plus b square, right? That
B
is what I have
square.
done.
Yeah.
Okay, for the
No,
numerator and denominator both. Yeah,
yeah. Okay, so we have done that separately for numerator and separately
right,
for
correct,
denominator.
correct, correct. Is it okay?
yeah, that was the cause of confusion. Means doing it separately gives me the absolute value for the ratio as well. Is that
Yeah,
like
that is the only way we have to solve it, right? Because here we have a complex quantity in the numerator as well as in the denominator. Okay. And that is the simplest
otherwise
also. Mhm.
if we do it like by rationalizing, like
No
means
need
with a complex
unnecessary.
conjugate?
No, no need.
Okay,
Unnecessary, it will make the problem very complex. Okay. Is it clear,
okay,
everyone? Satyam,
yeah, yeah.
Yes, ma'am.
Muthu, is it clear this one?
Yes, ma'am.
Okay. Now the
So
next
this
part of
is the
the
numerical value we have, right?
yes,
For
right.
sensitivity.
Correct.
Okay.
Correct.
What would be the unit for it, or how will we say, means how will we express it? Like this number represents the sensitivity, but uh, like transfer function with
It is
respect to
huh. It is
G.
yeah. It is, you can say, the sensitivity is like it is reduced by it is a factor. Okay. You can see here, this is gain here, G, uh, and H is the feedback gain. Okay. So it is factor, and it is like in most practical systems. Okay.
So can I express it like a 1% increase in G will lead to
Obviously it is,
2.88%
yeah, it is a
in T?
factor usually. Okay. So if it is greater than 1 means or it tends towards ones, then it affects the response of the system. Okay. And
So
it is
this
not
is means in percent
percent,
terms, this
it
is
is an
2.88 term.
right, 2.88
So
percent.
okay, a
That
one
is what we
percent
have
increase
written.
in G.
That is what we
Yeah,
have written, percentage change in transfer function by percentage change in G here. That is what I was telling.
G.
Okay.
Yeah, yeah. So and this number can also be negative, right?
This number can also be negative as we have
Sensitivity.
taken out the magnitude here. Okay. The percentage
This
will
can't be.
be, yeah. But when you see the second part of the question, where we have to find out the sensitivity of our transfer function with respect to H. Okay. If you derive that, that is percentage change in T by percentage change in H. Okay. If you derive this entire thing, you will get this as minus GH by 1 plus GH. Right? Correct?
Okay, okay.
But you are finding out the percentage. Right? And so if you
Mhm,
solve it,
mhm.
the magnitude, it comes out to be a positive number only. Right? You can, let us check it out here.
Okay,
I'm
okay.
writing it as finding out the sensitivity with respect to my feedback H. Okay. Then this becomes at, of course, j omega, where the value of omega is 1 and the value of k is 10. I'm just writing it down in single step. Okay. As we have seen earlier for the G, this will come out to be
Sure.
minus GH, that will be minus 5k divided by s plus 1 divided by 1 plus 5k s plus 1, and on solving this and putting all the values, what it will be, minus 5k divided by s square plus s plus 5k, and putting these values, what I'll get, let us see, minus 5k divided by 5k minus that will be omega square, right? And this will be plus j omega. So taking the magnitude at omega is equal to 1 and putting the value of k as 10, what I'll get? I'll get this 50 divided by 50 minus 1 whole square plus 1 square, right? I've just done the shortcut path. Okay. Is it okay? And now calculate the value. How much you're getting? That is Gaurav, please see the derivation of the sensitivity with respect to H. Okay. In the slides as well as you can see in the video lectures. Or you can proceed it in the same way as we have done for with respect to H. You can do it for with respect to G. You can do it with respect to H also, right? How much is the answer? Please tell. Are you done, all of you?
Ma'am, 1.01.
1.01. Okay.
Yes, ma'am.
I'm getting 1.020196. Okay, fine. All of you got this? Shall we move to the next problem?
Yeah, yes, ma'am.
We'll do one more problem, okay, based on this. Here, we have been given a closed loop configuration, okay. Just see this. Alpha. Then we have beta 2 divided by s square plus beta 1s, sorry, beta 1s plus beta 2, and this gives the output y of s, and this is a closed loop configuration having a feedback of 0.2 as this. Okay. Now for this closed loop configuration, we have been given the value of beta 1 as 4 and beta 2 as 9. For this, we have to calculate number 1. We have to calculate the sensitivity of our transfer function with respect to alpha, okay, where the transfer function t is y of s by x of s. Okay. Also, we have to find out alpha such that S alpha, the sensitivity with respect to alpha equals 0.2 in steady state. Okay. Is the question clear to all of you? Then we'll proceed further. What is the first step we should start with? क्या करेंगे सबसे पहले? Yes,
We have to find T.
correct. We have to find first of all t. So we have to evaluate t, which is the Laplace transform of output by input. Correct. So this is our forward path gain. This is our feedback path gain that is given to us. So we'll write and start our problem by finding Ts. That is Gs, right, upon 1 plus Gs Hs. Correct. So I can write down this as alpha into beta 2 divided by s square plus beta 1s plus beta 2 whole divided by 1 plus alpha beta 2 divided by s square plus beta 1s plus beta 2 and multiplied by 0.2. Correct? So on solving this, what I'll get? Alpha beta 2 divided by s square plus beta 1s plus beta 2 plus 0.2 alpha beta 2. Is it correct?
Yes, ma'am.
Right? Can I substitute the values of beta 1 and beta 2 here? So,
Yeah, yes, ma'am.
yes. So, this becomes 9 alpha s square plus beta 1 is given as 4. So, this becomes 4s plus 9 plus
1.8.
0.2 into, yes, 1.8 alpha. Correct? So, I got my transfer function, that is y of s by x of s. Now, let us find out the sensitivity of this transfer function with respect to alpha. Correct? So, I can start it like this. The sensitivity with respect to alpha, that is given as del t by del alpha into alpha by t. Is it correct? The very first principle which we have seen here. Okay. This with whatever parameter we are taking into account, right? That we have to incorporate in the expression. Is it correct, Gaurav? Do you get this?
Yes, ma'am. Yeah. So this is a general formula for sensitivity with any
Correct.
other with
Correct.
any input variable.
Percentage change in transfer function by percentage change in the parameter with which our system is affected, right?
Got it, ma'am.
Now this is my transfer function, so I have to differentiate it with respect to alpha, right? So it will be this denominator that will be s square plus 4s plus 9 plus 1.8 alpha, and differentiating this 9 alpha, d by d alpha of 9 alpha will give me 9, right? Minus 9 alpha, and differentiating the denominator. This will become 0, 0, 0, and I'll be left with what? Into 1.8. Is it correct? Whole divided by s square plus 4s plus 9 plus 1.8 alpha whole square, correct, into alpha by t. So if I see this t in the denominator, Here in the numerator, I'll be having s square plus 4s plus 9 plus 1.8 alpha. And in the denominator, I'll have 9 alpha. Correct?
Yes,
Okay.
ma'am.
And I can cancel out this term, right? I'm going with this first principle so that it becomes very much clear to you. Otherwise, we can directly use the formula and put the values and get the answer. Okay, that you can do it yourself. So on solving this, let us see what I'll get. 9 s square plus 36s plus 81 plus
Ma'am, can we take the 9 out?
from where? Here?
Yeah, the
Yeah,
numerator.
yeah. That will be simple, I guess. Isn't it?
The, it will cancel out the
Yes,
denominator.
yes. Yes, yes. It will cancel out. And this entire thing, 9 alpha into 1.8, isn't it?
Yeah, yes.
This thing cancels out, right? Divided by, and here we are left with 1 by 9, isn't it? And this is s square plus 4s plus 9 plus 1.8 alpha. So if we divide it by 9, we have s square plus 4s plus 9 in the numerator, and here we have s square plus 4s plus 9 plus 1.8 alpha. Correct?
Yes, ma'am.
So we got this sensitivity. Now, the second part is we have to find out alpha such that the sensitivity with respect to alpha is equal to 0.2, right? And this is very important in steady state condition. So what is the value of S under steady state conditions? That is equal to 0. Okay. Clear? So let us find out that under steady state conditions, when we see this sensitivity with respect to alpha, it comes out to be 9 by 9 plus 1 point alpha, and this is 0.2, which is given in the problem, right? So you solve the value of alpha, how much you will get, please? And tell me.
Two.
2.
Two.
All of you are getting that? Do you get the value of alpha?
Should
2.
it be 20?
Yes,
or
yes,
2?
20. Please check.
Yeah, yes.
Alpha comes out to be 20. Is it clear, this problem?
Yeah.
Okay. So here you have to take into account this now, at what condition it is given. Okay. So let us move on. And
Ma'am, when it says under steady
uh-huh,
state, we are
uh-huh.
not concerned with the kind of input that was provided.
Yes, you can here say that kind of input, like where the rate of change of any variable within a system comes out to be 0. It remains constant over a time in the steady state, right?
Mm, yeah, but
Input equals
when we
output. Huh.
sorry, when we studied error in steady state,
Mm-hmm.
we got different kinds of responses considering
Definitely.
different kinds of inputs like ramp or
It
parabolic or
will
step,
depend.
right?
Steady state error will depend on the system type and the input which we are giving. Here we are not talking about the error. You're mixing up two things. Okay?
No, I'm not mixing up. I'm just
Mm-hmm.
trying to draw analogy there.
Mm-hmm.
There, when we were working on errors, we need to know the kind of input that was provided to the system to
Correct.
ascertain
Right.
its steady state error, right?
Definitely.
But when we are talking about sensitivity, we are not concerned about the input, so to say. That's a question. Means
We
irrespective of kind of input, the sensitivity in steady state, the alpha value should be 20.
correct.
Okay.
Okay. Because see, we are doing the here we are for sensitivity. We are seeing the. You can see the first principle. We are looking at the change with respect to some variable, right? And if you're talking of steady state value, that rate of change, what is that? That will be 0, constant over time. There won't be any rate of change. Okay.
Yeah.
The derivative of a constant value is what?
0.
0. Okay. Is it
Okay.
correct, Gaurav?
Yeah, got it.
Okay. Now, let us take an example on the error coefficients now, which you were just talking about. Okay. Now, just note down the question and we'll just brush up what you have seen in the video lectures. Okay. If we have been given the forward path transfer function, of a unity feedback system as GS equals 5 s square plus 2s plus 100 whole divided by s square s plus 5 s square plus 3s plus 10. You have to determine the step, ramp, and the parabolic error coefficients. Okay, for the system. And also you have to determine the type of system. Okay, you have to find the step, ramp, parabolic, and then you have to determine the type of system.
Type of system is 2.
Type of system is 2, correct? Because in the denominator, we
We
have
have 2 poles at 0.
2 poles as 0. Very correct. So here our type of system is 2. What about the other details?
So since it is 2, we can say that the error coefficient for step and ramp will be 0.
Error coefficient. Error coefficient will be 0.
Yeah.
Error will be 0. Steady state error will be 0. But the error coefficient will be infinite. Yes?
Yeah.
Correct?
Yes. It is 1 by SGS.
Yes. So
1 by KV and 1 by
yes.
KA.
KP is given as your position error constant.
Coefficient 1 by
Coefficient, that is limit s tends to 0 GS HS, right? Our HS is here 1 unity feedback.
Yeah.
GS, I can write down this as 5 s square plus 2s plus 100. And as you can see here, I have in the denominator s square, s plus 5, s square plus 3s plus 10. So this tend towards infinity, right?
Yeah.
And if I see the steady state error, isn't it? That is
1 divided by 1 plus kp.
for step
Yeah.
1 by 1 plus kp. And this is 1 by infinity. That comes out to be 0,
Yeah.
right?
Yeah.
What is the interpretation of this? Can
So
anyone tell?
it tracks the step response without any error. Exactly means the way the input was provided, it will match that without any error.
Yeah, you can say this is an ideal tracking condition, right?
Yeah.
As in radars. Good. And now next is you have to find out for ramp. That is
kV.
kV limit s tends to 0, s gs hs, right? And how much it will come out to be again if I substitute the values? SS will get cancelled, and again this will come out to be infinity, right?
Yeah.
And steady state error, that is 1 upon kV,
Zero.
that is 0, right?
Yeah.
And the third one is the
So in case of kV, what would be the physical interpretation? Like it tracks the
it is
ramp input.
exactly, it is again ideal tracking because of our this transfer function is given in this way, right? Because I'm getting my coefficient as infinite and steady state error as 0. So this is also an example you can say which shows that there is ideal tracking.
So I'm just trying to
Mm-hmm.
take a physical world analogy. So if
Mm-hmm.
the rate of flow, incoming rate of flow of water in a tank, that's my input.
Mm-hmm.
And what should I say? The output. Output is again, let's say, another rate of flow of outgoing water.
Mm-hmm.
So I'm not sure if I'll be able to arrive at a ramp or this second order type 2 kind of system, but
Mm-hmm.
I'm
Okay.
just means
Yes, you can
this
try, of
this
course.
rate of input at the input side, the output will exactly track this rate of input. Is that what it means, or how shall I explain it?
For this, let us do a problem. Then you will be in a state to exactly tell whatever you're thinking is correct or not. Okay.
Okay.
Just wait for the next one.
Okay.
So now Ka, that what it comes out to be? S square
S square
Yes,
GSHS.
HS. And what I'll get here, let us see. S square 5, S square plus 2S plus 100 divided by S square, S plus 5, S square plus 3S plus 10. Okay. So how much it will come out to be? 500 divided by 50.
10.
That is 10. Right? Okay. And you can find out the steady state error. That is 1 upon K.
Yeah. 0.01, 0.1.
0.1. Correct?
Yeah.
Okay. Now let us take a real time example. As you
So
were just
this is the absolute value of error, right?
right, 0.1.
Okay.
Now, if I take this problem, okay, I'm drawing a block diagram of a electronic pacemaker, right?
Okay.
Let us see this. This is K by S plus 20. This represents my pacemaker. And here I have this 1 by S. This transfer function or you gain represents my heart. Okay. And This is output CS. This is input RS. Yes, I have to draw a summer point first here. That is important. This is RS, and this is my unity feedback in order to minimize the error here, right? So you have to determine the steady state error here. Find steady state error for unit ramp input when K is equal to 400. Also find the value of K for which steady state error to a unit ramp will be 0.02. Now let us see this problem. Okay. Is the problem clear?
Yeah, one question.
Yes.
How did we arrive at the model for heart? Like it is
That model for heart has been given to us. Okay.
yeah, it might be beyond the scope of the question. We are given and we can do the what is asked to us. But in realistic settings, how do we arrive at such models? Like just briefly, if you can tell.
Yes.
Maybe not about heart, but a simpler thing, if that is.
See, we can model all the systems that exist, like the pneumatic systems, the mechanical systems, electrical systems, hydraulic systems, by relating the input and the output, right?
Okay. So
As you might have seen in the previous weeks, no, in the lectures, you might have seen that everything can be modeled with the help of the mathematical equations.
Yeah.
Right. So this is how the gain, or you can say the transfer function for the heart, has been given as 1 by S.
Okay.
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 And for the pacemaker, it is given as K by S plus 20. Okay.
Okay.
We'll look into the details of more of this, that how to go to the real time and real world examples.
Okay, ma'am.
So now if I see here, for unit step ramp input, I have to find the steady state error. Okay, so what will be RS here?
RS is 1 by S. Sorry, 1 by S square.
Right. RS is 1 by
S square.
S square.
Yeah.
HS comes out to be 1. It is evident, as we can see from the block diagram. Right. And if I find out my GSHS, it will be how much? K S into S plus 20. Right?
Yeah.
So if I now look into my steady state error, that is limit S tends to 0. As we are talking of the ramp input, it will be S into RS 1 plus GSHS, right? Correct?
Yeah.
That is limit S tends towards 0, S 1 by S square into 1 by 1 plus K S plus 20, right? So now solving this, what I'll get? Limit S tends to 0, 1 by S plus 20, S plus 20 plus, shall I substitute the value of K as 400 here? It is given, correct?
Yeah.
So what will be the value here on solving? 5?
I got it as 0.02.
This is, see, please check.
Yeah, I actually used the method that we used in our last problem. Means for KV, I calculated KV directly using limit S tends to 0 S GSHS.
Okay.
And have I done any mistake? GS. So KV will be equal to limit SGS S tends to 0. Am I right?
That is KV. We have to find out that is correct. Very
Yeah.
correct.
So
We are finding
KV
the,
means error will be 1 divided by KV.
yes,
So I am getting KV as 20. So 1 divided by KV.
1 by 20 is 0.05.
Yeah. Okay. Yeah. Fine. Sorry.
Fine.
Yeah.
Okay. So similarly, you have to find out now the value of K for which the steady state error is given as 0.02. Can you do it yourself? Your steady state error is 0.02. Okay. You can use both ways. So what will be KV and then you can solve, or either you can use this. Okay. So I'm just giving you a minute to solve this and tell me the answer.
Could you repeat the question, ma'am?
Yes, we have to find out the value of K for which the steady state error to unit ramp is given as 0.02. Done? Anyone got the answer? Up till here, it is going to be
1000.
1000.
Yeah.
1000 is the correct answer. S plus 20. Okay. So all of you got the answer?
Yes, ma'am.
Muthu, did you get it?
Yeah, yes, ma'am.
Okay. Okay, you just do one. Let us see one more problem. Like uh, for the unity feedback system, our GS is given as 20 by s plus 2 s square plus 2s plus 20, right? You have to find out the steady state error of the system when the inputs are 5t. First, for the first case, let it be 5. Then the second case, you have the input as 5t. Then third, you have input as 3t square by 2. Okay. So you have to calculate the steady state error for these inputs. Okay. So again, how we'll proceed? You see, that's why, Gaurav, I have done here like from the basic expression, rather than putting like KV or like KP or K. Okay. Uh, the step input, ramp input, and parabolic input are our like standard functions, right?
Yeah.
Now, yeah, if we have this input or say the variable inputs, how will be finding out the error? Okay.
So we are given the forward transfer function GS, and it's a
Right.
unity feedback.
Right. Right. So for the first case, when we have been given our input, we have taken like for all the systems as RS, like our Laplace transform of the input, and CS as a Laplace transform of the output. So if we write in time domain, it will be R of t, correct? And this can be written as 5. So what will be RS then? Yes, 5 by S.
Yeah.
So the steady state error, that will be limit S tends towards 0, S, RS, or 1 plus GSHS. And what is this entire thing? This is nothing but our
Error.
error ES, right?
Yeah.
Correct? So let us put the values and see what we'll get here. The error as S tends to 0, S, RS is 5 by S, then 1 plus 20 by S, S plus 2, S square plus 2S plus 20. So on solving this, what we'll get? Limit S tends to 0, this gets cancelled, and numerator will have 5S, S plus 2, S square plus 2S plus 20 whole divided by S plus 2, S, S square plus 2S plus 20 plus 20. So putting the values, our steady state error will come out to be 0. Correct? Right?
Ma'am, in denominator, we have S into S plus 2. Okay, we have a plus 20 term there.
Right,
Okay.
right.
Yeah, yeah. So, yeah, numerator, we have a single S, so that will make the entire error go to 0.
0. Correct?
Yeah.
Now for the second input, which is 5t, what will be the Laplace transform of that? 5 by S square. Okay. So again, put the values and find out the steady state error. And let us see what we'll get. So this is s into 5 by s square into 1 by 1 plus 20 s plus 2 s square plus 2s plus 20. So on solving this, this is 5 by s into s plus 2 s square plus 2s plus 20 whole divided by s plus 2 s square plus 2s plus 20 plus 20. Correct? So this gets cancelled. Limit s tends to 0 of course. And how much you will get? 5, 2, 20. This entire thing will become 0 plus 20. So this comes out to be 10. Right?
Yes.
Yes. Now the third input is what? Third input is,
Parabolic.
yeah, 3t
3t
square by
2.
2. Right? So what will be its Laplace transform?
3 divided by 2 s cube.
Correct. Okay?
S cube in the denominator.
Yes, yes, correct, correct. Correct. S cube in the denominator. Now it is okay?
Yeah.
Okay. So find out the steady state error. S into 3 by 2 s cube into, shall I write it directly over here?
Yeah.
S plus 2 s squared plus 2s plus 20 whole divided by s plus 2 s squared plus 2s plus 20 plus 20. So on solving it, what we'll get? See, here 3 by 2 s, and this is 2, 20, 0 plus 20. Correct? So since we have s in the denominator, this comes out to be infinite. Correct?
Yeah.
So you could see that how the steady state error of the system varies and depends on the inputs, right?
So this is a type 1 system, right?
This is a type 1 system, right? See, if we want to generalize, right? Now, if we want to generalize for, say, uh, as you might have seen in the like videos, like for unit step, if you're talking of, see, as your type of system, okay, type 0, type 1, type 2, right? If we talk of this, then for unit step, what is the like position error constant? What it will be for type 0 system? Have you
KP. KP.
KP,
Yeah.
right?
Yeah.
And what will be the error there?
1 divided by 1 plus KP.
Correct. 1 by 1 plus KP. And for type 1?
Infinite.
No.
For unit step.
Unit step I'm talking of.
Okay. Input is unit step. So it will be 0.
0. Type 2? 0.
0.
Right. Now, again, like, let me see for unit ramp. Okay. What it will be for unit ramp?
Type 0 will be infinite
Correct.
and error
Type
will be
1,
1 by kV
and this will be again
0.
0. And if I talk of like a unit parabola, what it will be?
Infinite
Infinite, and 1 by
K.
k. Now let us analyze this as you was asking. Now, if I see here, right?
Yeah.
If for type 1 system, if I see here, like I'm getting only the error here as 1 by kV. Okay. And this as infinite for type 0 system, this for unit RAM. So this is, I cannot track this. This is cannot be tracked. Okay. Not trackable. And if this is 0 for type 1 system, you try and understand this. If the error is 0, that means you can perfectly track that system, right?
Yeah.
Tracking error is here 0. You can perfectly track, means the output is perfectly following the input and the tracking error is 0. Here also it is not trackable, right? So where the error is 0, you can perfectly track it. The example which you was giving, Gaurav, for that like water tank,
Yeah.
okay, the rate of flow at the input side should be equal to the rate of flow for the output side for error to be 0,
Yeah.
right?
Yeah.
Then only you can say there is no tracking error, right?
Yeah. Yeah.
Okay. So let us do one more problem.
I was
If
actually trying to
Mhm,
seek out an example of
mhm.
a type 1 system.
Type 1 system
Yeah. Where there is a constant error for unit ramp.
for unit ramp. Okay. I had one problem based on that now. Well, exactly what you're telling.
I mean, what means problem solving and that calculation is very clear now, having
Mhm,
gone through these couple of
mhm,
examples.
mhm, mhm.
But the physical system, like,
Okay. Let us do one. I got your point. Let us do one problem based on that now. Okay. So see, we'll take this example of a servo mechanism. Okay. There is a servo mechanism which is designed to, it is, let me jot it down so you get the things clearly. Servo mechanism is designed to keep a radar antenna pointed at a flying aeroplane. Okay.
okay,
Okay. Now, if this aeroplane is flying with a velocity of 600 kilometer per hour at a range of uh, say 2 kilometer, and the maximum tracking error um, is to be within is to be within 0.1 degree. You have to determine the required velocity error coefficient. Okay,
That means KV, right?
correct. You have to find out KV.
Okay.
Okay. And the block diagram of this servo mechanism is given to us.
Yeah, one question here.
Yes, yes.
So velocity error coefficient, that will be a number, right?
Right. That will be a
And
number.
yeah, so if that is not a non-zero constant,
Mm-hmm.
so the error will be reciprocal of that. So again, that will be some number.
Right.
Okay. So okay, yeah. Please proceed. Maybe that will at the end, when we'll compare the input or what exactly the input is with the
Mm-hmm.
output, we'll get to know what does error mean.
Yes. Yes.
Okay.
You can see this.
Sure.
This is a good example that I guess will clear your doubts. Okay. Now see, if I'm talking of this entire example, and the servo mechanism is represented by this block diagram, I have to find out, right, the velocity error coefficient, which is going to be KV. Correct?
Now this transfer function is given to us, or can
That is
we interpret it
that
you
is
from
given to
the
us. This is given to us. This servo mechanism is given to us, and this servo mechanism is designed to track the flying aeroplane by the help of that radar antenna, right?
But let's say if I'm not given this transfer function, I
Mm-hmm.
just know this problem statement.
No, you have to have this. You have to have this to solve the problem,
Okay, fine.
or otherwise the gain of that servo mechanism should be given in the problem as such. Okay, then you
Gain
can
of the servo mechanism.
mechanism.
So
Okay,
that
that is
gain
gain
is
kv by s1 plus st, and that servo mechanism is a unity feedback system, right?
okay. Okay.
Correct.
So my intent is that I just know the geometry, or maybe trigonometry, whatever you would like to call it.
Yes.
And with basic laws of physics, I want to determine that gain function. Is that possible?
Right, yes, it is. We use all that analogy for the physical systems, and we draw analogy between physical systems and the how to write in terms of electrical like notations. That is what mathematical modeling is, right?
Okay. Okay.
So see, um, now since our aeroplane is moving with a constant velocity, right?
Yeah.
So what will be this RS? This RS is going to be a
S
ramp
square.
function.
Yeah. Ramp 600 by S square.
No, this is like, no, this 600 is our linear velocity,
Yeah.
right?
Yeah.
This is our linear velocity, which is given to us as 600 kilometer per hour. Now you can see here that at a range of 2 kilometer. Okay. So you have to change this into angular velocity. You know that V is equal to R omega.
Yeah. But why do we have to do that?
We have to do that because it traces, you have to find out the tracking error in terms of your degrees, right? So you have to have the velocity in radians or that or degrees, then only you can track it, right? The steady state error has been given in this. Okay, so you know that V is equal to R omega, the relationship between linear velocity and angular velocity. So
Yeah.
omega will come out to be 600 by 2.
1000. Sorry, 2. Yeah.
Okay, since our this range of 2 kilometer, that we can take as R. Okay, Your R
And
is,
what do we mean by range? Like the point of measurement and that flying object.
yes, the range means you can say the radius for which your aeroplane can be tracked by this antenna, right?
Oh, okay.
Correct. So this comes out to be 300 radians per hour. Now convert it into radians per second. How much it will be? 300 by 3600 radians per second. So how much it will be?
1 by 12 radians per
1
second.
by 12 radians per second. Correct. Okay. So once we got this angular velocity, this will be acting as our input, as RS will be 1 by,
One question here.
yes, yes, yes.
This is the angular velocity of that flying object, is it?
Correct. Correct.
But that flying object, that aeroplane goes in a straight line.
Fine.
So this angular velocity, can it be constant?
Can it be?
Constant.
So see, since aeroplane is moving with constant velocity, that's why we are taking it RS as a ramp function, right? Fine. With a velocity of 600 kilometer per hour at a range of 2 kilometer.
No, our input, this RS in this system, this
Right.
RS is angular velocity or linear velocity?
This RS is our angular velocity.
Okay. Now
Because
my
see you,
question is that the linear
uh-huh,
velocity is constant, that is 600 kilometer per hour.
yeah,
Okay. How can be the angular velocity constant?
we have converted into angular velocity for the given range of 2 kilometer. So it is
And
going
this
to be
angular velocity is at that specific
range,
2
within that
kilometers.
specific range.
No, no, no.
Correct.
That's
Correct.
where the interpretation of range, I believe, is different. Means my what I am getting from range is that at at the point, at the instant of measurement, that aeroplane from the radar, the distance between radar and that aeroplane is 2 kilometers. Is that correct?
The distance between the radar
Radar
and,
and the aeroplane is 2 kilometers.
I guess no.
And if that is not correct, then how can be angular velocity a constant?
It is aircraft range when you talk of, it is always going to be a constant.
Okay,
Okay.
I'll give you one short example.
Okay.
Correct me if I'm means if this does not, that analogy doesn't fit here. Okay.
Mm-hmm.
I'm standing from a railway track. I'm standing at a distance of 100 meters.
Mm-hmm.
Okay. Now a train is approaching me. Means,
Mm-hmm.
of course, train is running on the track. Train will not directly hit me, but it is coming on that track. It is running on that track. Let's say at a speed of 60 kilometer per hour.
Mm-hmm.
The train speed is constant, 60 kilometer per hour.
Mm-hmm.
Okay, and the distance, the normal distance, the perpendicular distance between the track and me is 100 meters. That is again constant, means it's fixed, right? But when I am tracking that train,
Mm-hmm.
if the train is really far from me right now, the movement of my head will be slow, and
Mm-hmm.
as it approaches me, I'll move my head really fast, and then the train will leave away, right?
Mm-hmm.
So the angular velocity at which I am rotating my head, that is not constant, right?
That is correct, the analogy which you have given. But then we
And
are talking about the range of an aircraft where R is the range and V is the velocity. And here we are taking that it is going to be constant for the given time.
Yeah, so
right?
I am
For a
trying to
given time.
understand the meaning of range here. So if my interpretation of range is okay, I think Muthu has something to say.
Yes, yes, Muthu. Yes.
Yeah, yes. I think here some things are to be assumed to go with this.
Correct. Correct.
Like Gaurav sir said, the range must be the distance from the radar end to the plane, but the plane should go to directly top of the radar for it
Correct.
to be, yeah, and it
Correct.
should go from one
It,
side to
it
the other. It should
it
cross
need
the.
not be. That's what I'm trying to. I mean, the question still fits my analogy, but when we consider that at that very specific instant, the tangential value.
That will also come into picture. But as Muthu has said, we have to assume for this problem. Okay. So
And
And
ma'am,
that assumption might not be like it need to be directly on top of that radar. It can be at some oblique angle. Even
it
that's
may
fine.
be.
Yeah,
It may be.
even that's fine. But uh, the angular velocity at that very specific instant, that will be constant. I agree. But
But
um,
over
that is
that,
what we have to consider for solving this problem. Whatever you're telling is fine. But then for this problem, we are assuming that it is moving with constant velocity for a particular instant of time. And that instant, we have to find out what is the like error coefficient for the maximum tracking error to be within 0.1%.
I
Okay.
mean, this interpretation of range is actually, I mean,
Yes.
along with
Someone
the
wants to
assumptions.
say something?
yeah, yes, like Gaurav sir said,
Mm-hmm.
for the angular velocity to be constant, the in
Mm-hmm.
the railway
Mm-hmm.
train and person observing it,
Mm-hmm.
we should assume we are in the center.
Mm-hmm.
The track is circling, or the track is a circle with us being on the center. And
Yeah, you
That's actually a different scenario altogether. Then
yeah,
we are tracking a satellite just on means which is revolving around the Earth.
Earth,
yeah,
right?
Right?
so
That's a
again, this
different situation.
question must be made in that sense, I believe. The so that the angular velocity can be constant, but since we are assuming the path as circular instead of straight,
Yeah,
the actual angular velocity must
Yeah,
be
yeah.
little higher than the calculated one.
yeah. We can assume it like this, right? This is our aircraft, and this is we can assume the direction of the flight path, right? And
Okay.
this is our say center, and this is going to be our range R, right? As Muthu has said, for our railway track, we can be at center, and the railway track can be circular. I guess you are talking about this, Muthu.
Yeah, yes, ma'am. But
Okay, so we'll
here,
we'll go
only
with
thing is
this
it is not a circular
Okay.
path; it is in the straight. So,
straight, right? Right. Okay,
but we still the radar should rotate so that the angular velocity comes in. But
correct.
since the plane travels straight, which it needs to cover in as an arc
Mm-hmm.
for which we are calculating, the
Correct.
angular velocity, original angular velocity will be little higher
Little
than.
higher. Correct. And that's why it is within the maximum tracking error is given in degrees, right? From here, you have to make the assumption that it is going to be a circular thing, right?
Okay. Okay.
Okay, very good discussion. Everyone is giving a thought and correlating control systems with real time examples. Very nice. Good discussion. So, RS comes out to be 1 by 12 S square. If you solve it in how much it comes out to be in decimal? 1 by 12?
0.08 something.
83 or 0.083 by S square, right? So now the steady state error, that will be limit S tends towards 0, SRS into 1 by 1 plus GS HS, and you can substitute the values here. S 0.083 by S square into 1 by 1 plus kV S 1 plus ST. Okay. So now for the steady state error to be 0.1 degrees, you have to find out this velocity constant. Okay. So limit S tend towards 0, 0.083 by S into S 1 plus ST, S 1 plus ST plus kV. See on solving how much you're going to get here.
Again, one thing, the velocity is in radians per second and the error is in degrees.
Mm-hmm.
We'll have to convert degree into radians or vice versa.
Yeah. You solve and tell me how much you're getting.
One degree was the given value, right?
Yes, 0.1 degree, I guess. Or 1 degree, 0.1 degree.
0.1.
0.1.
Ma'am, what is ST here?
Here it is given. See, ST.
It's just a random variable.
Mm-hmm.
Okay.
We are supposed to find the value of kV, right?
Mm-hmm. Right.
It comes out to be 3.1416.
3.1416.
1416.
Everyone is getting that?
I
kV.
might be wrong. Yeah,
kV.
kV, yes.
You have converted degrees into radians or radians into degrees?
Degrees into radians.
And what is the value in degree?
I've converted degrees into radians. So degree is 0.1 degree. That is what we are given, right? Error.
kV, you tell me how much kV is in degrees per degree. How much is that?
So, okay. In degrees, it means in radians, I'm getting it as 3.1416.
Mm-hmm.
That's in radians, and in degrees, it will be
You multiply it by 180 by pi.
yeah. $2735.67.
You have done some mistake somewhere. Check it out. On converting this, how much it was? 1.1 degree?
That will be pi by 1800.
Pi by 180. That is
Pi divided by 1800.
1800. No, it is pi by 180. Why it is
Yeah, means
1800?
0.1 means you will
Okay.
take 1
Correct,
0.1,
correct.
right? So
Okay.
pi divided by 1800.
And 0.083.
Yeah, so that is like 1 by 12 if you do
kV.
not. Yeah.
So what is kV?
kV will be
I think, is it coming
How much?
around 50 mem or
51.
47 point something,
47.56
.56 radians.
radians. And if again I ask you in degrees, how much it will be? It will be less than 1 degree, right? Because 1 radian is around 57 degrees. Okay. You convert it into
but these are 47 radians, so it will be 47 into 57.
okay.
So if you carry along with your calculation, pi
Mm-hmm.
divided by 1800 is equal
Mm-hmm.
to,
Mm-hmm.
so that will give kV like 1800 divided by 12 pi.
You are getting the same answer?
So 1800 divided by 12 pi, that gives me 3.1416 radians.
Okay. Muthu, you are getting the same answer?
And
No, I didn't convert it to degree yet. In
yeah,
radian,
so,
I'm getting this.
so if I convert it to
Okay, fine.
16 into
Fine, this is good to go. Okay.
179
Yes.
degrees.
Okay.
In degrees it is 179 or 180
Oh.
degrees.
Yes, yes, correct. So let us do now some problems on this controllers. Okay.
Okay.
And stability. I guess the time will be we will be short of time. Shall we do the problem on controllers or okay, let us do a simple problem on controller here. The proportional control, integral control and derivative control. Okay. You might have gone through the content. Yes?
Yeah, yes, ma'am. Regarding the thought experiment we did for the last question, the train analogy, right? Gaurav sir said. Yeah, there it will be for sure we will be having different angular velocity only. But here in this question, since it is mentioned to keep the range constant.
Correct.
I think here the aeroplane itself is going in a circular path.
Of course, that is how we calculate like the tracking system for radars and aircraft.
So here we are not making any assumptions also, I think.
Correct, right.
This, so yeah, yes.
Okay. So
actually, if that is the case, Muthu, then even radar will not have to change the direction. Like it's in case of a geosynchronous satellite. Anything right above you will stay above you because the earth is rotating, right? So radar will not have to turn its angle, right?
No, could you repeat again, sir?
Yeah, so if it isn't, means if you consider a case of a geosynchronous satellite, where the satellite actually moves at a constant angular speed, and that matches with the speed of rotation of Earth,
correct.
right? So if you are looking just at it, you will keep looking at it. You will not have to move your head, right?
Yes.
Yeah.
Correct.
So even in this case, I believe the angular velocity is a function of the position. And since we are considering the range, again, the interpretation of range is my interpretation is that at that specific instant, when the radar and aeroplane were 2 kilometers apart, At that specific instant, the angular velocity is some constant which we arrived at.
Okay,
But
okay.
as the range changes, the angular velocity will change.
Yeah, of course. Yes.
Yes, we can. Yes, we can discuss it like now on the forum and all. Let us go to the next problem. Otherwise,
Sure.
like we won't be able to complete all the topics.
Yeah, sure.
Okay. Uh, so let us do this problem where we have a unity feedback loop containing a minor rate feedback loop. Okay. We can start with the block diagram here. This is RS. This is CS here. And we have this as our rate feedback loop inside a unity feedback loop. It is like this. Okay. So we have unity feedback loop, and we have a minor rate feedback loop. Got it? Now, without any rate feedback, so if we say that B is equal to 0, that is without
What's the sign for that rate feedback loop? Plus or minus?
here, this
Yeah.
one, this is minus. Okay. You have to determine the damping factor. Then you have to find the natural resonant frequency, overshoot of the system, to unit step input, and steady state error that results from a unit ramp input. This is your part 1 for this given problem. And the second part says you have to find the rate feedback constant. Rate feedback constant, which will increase your equivalent damping factor to 0.8. Also, for this case, you have to find out the overshoot to the system to a unity step input. That we'll see, that I'll tell you. Let us first complete part 1 and this, which is given for part 2, and then we'll proceed further. Okay. So can you get the system, and did you get what is being asked? Is it clear? Yes. For the first case, when there is no rate feedback, okay, means there is no this is not present. You can simply write down what is your transfer function, that is CS by RS. Yes. for B is equal to, when B is equal to 0.
0.
And you can find out the given parameters. You can find out the damping factor, resonant frequency, and overshoot. Okay, what it will be? We can just see CS by RS is equal to GS by 1 plus GSHS. Okay, so 16 by S plus 4 divided by 1 plus 16 S plus 4 into 1. Okay, so this comes out to be 16 by S square plus 4S plus 16. Now we can compare this with a standard transfer function for a second order system, which says that it is equal to omega n square by S square plus 2 zeta omega ns plus omega n square, right? So omega n square is how much? That comes out to be 16, which gives our omega n to be 4 radians per second, right? That gives us the natural frequency. 2 zeta omega n is equal to 4. Okay, so how much is zeta?
1 by 2.
That is 0.5, right? Clear? So you have been asked the natural resonant frequency. Okay. So
That is omega n, right?
yes, and you have to
Peak
find out
overshoot.
peak overshoot, that you can find out what it will be. MP, that is equal to e to the power minus pi zeta by root over 1 minus zeta square. If on substituting the values, what I'll get, find out. Okay, and then steady state error. We'll do those two questions after this, Muthu, okay, which you have asked now. Otherwise, it will also be pending. Okay,
Yeah, sure.
RS 1 plus GS HS. Okay, and HS is 1 over here. So limit S tends to 0, S into what is the input unit ramp, right? 1 by S square, 1 plus 16 by S into S plus 4. On solving this, see how much you are going to get. S plus 4 plus 16. So it is 4 by 16, that is 1 by 4. And what is the peak overshoot you are getting? Have you calculated this? Anyone? Point 0.5 pi divided by 1 minus 0.5 square into 100. Please tell the answer, how much you're getting. Yes, be fast. Gaurav, have you calculated this?
Doing it.
Okay. Muthu, how much you're getting?
E power minus 1.8, sorry, 181.28.
No, you calculate it.
Yes.
You cannot leave it like that.
it 0.16?
Correct. That is in percent, you will get it as 16.32%, right?
Yeah.
Getting it? Now, see, in the second case, you have to.
Ma'am, I am getting 0.90448.
No, you please check it. This is a correct answer. I've calculated it. Just double check it, okay? Later
What
on.
is the what answer was told, ma'am?
This
What was
is
the answer?
16.32.
16.3.
0.1632. Okay?
Okay.
Check it
Okay.
later on.
Let me.
Right?
Yeah. Sure.
Okay. Now see, the next part, you have to determine the rate feedback constant. That is you have to find out the value of B. Okay, this is the rate feedback constant. You have to find out the value of B which will increase the equivalent damping factor of the system to 0.8. Okay. That is zeta will be equal to 0.8. I'm just telling you the how to solve it. Okay. And you solve it, and if you have any doubt, you ask me in the next class. Okay, because we need to solve those two problems also. I'm just telling you this now. If we are considering the feedback, this loop, okay, if we are considering this feedback, right, this will be, you solve it as 16s s plus 4 taking bs into account, and then again you solve for cs by rs. Could you do it yourself? It will come out to be 16 by s square 4 plus 16b into s plus 16. I'm just telling you the steps. Okay, you compare it with the standard equation. Omega n square will be 16, which will give you the value of omega n to be 4. Now, in this case, theta omega n will be how much? It will be 4 plus 16b, right? And the value of this damping factor of the system increases to 0.8. So zeta will be here 0.8. Okay. So substitute it here. Get the value of B. I'm telling you, B you will get as 0.15. Right? Get the value of maximum overshoot. Okay. And also find out the value of steady state error. Okay. This is your, you have to do it yourself. Okay. So shall we go to those two problems which has been asked by Muthu from graded assignment 4? You have to say, I could not see when I'm sharing the screen, I could not see who's raising hand and what you people are saying.
Sorry, it was me.
Yes.
We can go to the problems, but I just rechecked my calculation. I'm still getting like 90% for the peak overshoot.
This one? This one?
Yeah.
You please do it once again. I have to see the calculator, setting and all. Okay. So question number 3. You have question number 3 with us. Open loop transfer function with unity feedback GS with unity feedback system having GS as K by S1 plus TS is given, right? For this system, overshoot reduces from 0.6 to 0.2. Overshoot reduces from 0.6 to 0.2 due to change in this K only. If K1 and K2 are values of K for 0.6 and 0.2 respectively, then which expression holds true? This is a question, right? Okay.
Yes.
So how you have to proceed? First, you have to find out the closed loop transfer function, right? That will be GS by 1 plus GSHS. Okay. On solving this, how much you got? If you have the calculation, you can tell me quickly. K by S 1 plus Ts divided by 1 plus K S 1 plus Ts, right? So this will come out to be
K by K plus
K by,
S
yes,
into 1 plus T.
this is T into S, right? So it will be S plus S square T plus K, right?
Yes.
Or I can write down this as K by making the coefficient of higher order as 1. This can be written as T S square plus S by T plus K by T. Can I rewrite this as this?
Yes.
Or K by T divided by S square plus S by T plus K by T, right? Now, if I compare it with the standard form, which I've just seen, that is omega n square by S square plus 2 zeta omega n S plus omega n square, I can write down omega n square equals to K by T, right, Muthu?
Yes, ma'am.
That is, omega n will be how much? Root
Root of
over
K.
K by T, correct?
Yes.
And 2 zeta omega n will be how much? That is 1 by T,
By T.
correct?
Yes.
And zeta will be 1 by 2 omega n into T, correct?
Yes.
And now, can I write down 1 by 2 this omega n as root over K by T? And if
Yes.
I take this T inside the square root sign, it will be T square,
T square. Yes.
right? So this will be 1 by 2 root over KT,
K T. Yes.
correct?
Yes.
Okay. So now coming back to this for peak overshoot of 0.6. Okay. I can write down for MP is equal to 0.6. Peak overshoot as given as e to the power minus pi zeta by root over 1 minus zeta square, or 0.6 equals e to the power minus pi zeta 1 divided by root over 1 minus zeta 1 square, correct?
Yes, ma'am.
Okay, fine. I'm taking this as zeta 1, this as zeta 2, right? So now I'm doing all this to reach to the given result, right? Now, can I take log on both sides, natural logarithm? Okay, so minus pi zeta 1 by root over 1 minus zeta 1 square, and log of e will be equal to 1, right? On solving this will give me minus 0.51 equals minus pi zeta 1 by root over 1 minus zeta 1 square, right? Now, if you solve for the value of zeta 1 here, what you will get? Please check it. Huh? I'm telling you, I have solved it
Yeah, sure.
for, yeah, when I have prepared this 1.1602, right? Do you get it up till here? Have you solved it like this?
Yeah, yes, ma'am. I think, yeah.
For
I
M,
actually left it
Huh.
in the form of K1T.
No,
I
no.
found out the value of K1T
Yeah.
instead
For
of
MP 0.2, again, you do the entire process.
Okay.
Okay, from here to here. And you will get your zeta 2 as 0.4559. Okay, correct?
Okay.
Now, for zeta 1, your k is equal to k1, and for zeta 2, your k is equal to k2. It is given like that? Yes?
Yes,
Yes,
ma'am.
ma'am.
So, zeta 1 will be 1 by 2 root k1t. That is how much? 0.1602. Correct? So this is
Yes.
your equation number 1. Similarly, for zeta 2, 1 by 2 root over k2t is equal to 0.4559. Correct? This is equation 2. So now take the ratios of zeta 1 by zeta 2. What you will get? That will give you can see root over k2 by root over k1 or root over k2 by k1 is equal to, you have values of this, divide it, zeta 1 by zeta 2, you will get 0.35, right?
Yes.
Okay, now square both the sides. So you will get k2 equals 0.1225 k1 on squaring both sides. Okay, it
Yes,
is a
ma'am.
bit like a lengthy problem, but it's easy, conceptual, it's not difficult. Okay, so now from equation number 1c, from 1 root over k1t, I'm just doing shortcut, you elaborate it and check it. Okay, that is 1 by 2 zeta 1. Okay, that will give you 3.1210. Okay, or k1t will be, yes, 0.9741, right? Or Tk1 minus 1 will be 8.741, subtracting 1 from both the sides, right? Similarly, from 2, you will get root over k2t as 1 by 2 into zeta 2, that is 1.09673. And k2t will come out to be 1.2028, and tk2 minus 1 will come out to be 0.2028, and the ratio, if you find out, that will give you 43.3. Okay, that is, I guess, was your option C, no? Yes, option B. Got
Yeah,
it?
yes, ma'am.
So you please do it elaborately. Okay, I've told you the steps and the method. And what was question 4? A system was given to you, right? This
Yeah,
was a
yes.
system
Okay.
with output, input, k by s plus alpha, right? This is a first order system, and the response to a step input is shown in the figure. Okay, do you have question with yourself?
Yes, ma'am.
Okay, all of you. So I'm like just drawing it roughly.
Yes, ma'am, we have.
Okay, okay. So this is 2. This is C of t. Okay, this is how much is the value at this instant? It is 0.2. This is 0, and we have this as C of t. It comes down like, it is like this, right? This is C of t, correct? And this is time in seconds. Okay, so you have to find out alpha and k, this alpha and this k. Fine. So if I write down the transfer function Cs by Rs, how much it will be? This is an open loop transfer function, right? Okay, so it will be k by s plus
Yes.
alpha simply. Okay, and see, it is given that the response to a step input. So what is Rs here? Yes, Muttu?
1 by S.
Correct. 1 by s. But you see the step response here. What is the magnitude given here?
2.
2, correct. So it is 2 by s. Okay, both the things are interrelated. It responds to a step input shown in figure. So the step input here is having a magnitude of 2, right?
Yes,
Got it? So now what is my CS? Rs is 2 by s. So 2k by s into s plus alpha. Okay, so I have to solve it using that partial fraction expansion. That is I can write down this as A by S plus B by S plus alpha. And on solving this, I'll get A as 2K by alpha and B as minus 2K by alpha. Did you solve it like this?
Yeah, yes, ma'am. Yeah.
You were getting up till here?
Yes, ma'am.
Okay. So this is what 2K by alpha by S minus 2K by alpha by S plus alpha. Correct? So
Yes.
now if I take the inverse Laplace transform, what it will be? Taking inverse Laplace transform, C of t will be 2K by alpha. Okay, inverse of 1 by S is 1 minus 2K by alpha e to the power minus alpha t. Okay, 1 by
Yes.
S plus A is e to the power minus at, inverse Laplace transform of that. So this can be written as 2K by alpha 1 minus e to the power minus alpha t. Correct? Now
Yes.
see again, you have to see this response. What is the steady state value?
2 or around 2.
This is going to be constant. Yes. This
Yes.
will become 0. Yes. This consists of two terms. This is the steady state value and this is a transient. Right?
Correct.
So the steady state value, if I see steady state value of C of t, that is at infinity. Gaurav, is it clear? Are you getting it?
Yes,
At
ma'am.
infinity, this becomes 2K by alpha. Right? Now see here, what I have to do, I have to find out the slope. Okay, that is C dot t. What it will give me? For this? Yes?
So we need to derive it.
No. Yeah, you just find the derivative of it. C dot t. That is a slope of the system.
Minus 2k e to the power minus alpha t.
Minus 2K alpha into alpha minus of minus, it will come out to be, no?
Plus, yeah.
Right?
Yeah.
E to the power
Minus
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 alpha t.
alpha t. Alpha gets cancelled. This becomes 2K e to the power minus alpha t. Correct?
Yes, ma'am.
Fine. Now, if I say the value of this derivative at t equals 0, how much it will be? E to the power 0 is 1. This comes out to be 2K. Right?
Yeah. Yes.
Correct?
Yes, ma'am.
Yes.
So, 2K by alpha, you can say it is equal to how much? That will be equal to
2.
Yeah.
2.
Two.
2.
Yeah.
Yeah.
Yes.
That's a steady state value.
Yes. 2K by alpha is equal to 2. So 2K is equal to
10.
10. Right? And
Yes.
K is equal to 5. Right?
Yeah. Yes, ma'am.
Okay. So shall we stop here today?
Ma'am,
Yes.
how did we get alpha equal to 5? Sorry. In the last step.
2K is equal to 10, right? K
Yeah.
is
So
equal to
that's
5.
2k is equal 2k by alpha is equal to 2.
So K is equal to alpha.
Yeah. K is equal to alpha.
And 2K is also equal to 10.
Is that given?
You see that the value, the steady state value, that is equal to 10. When you find out the slope at t equals 0.
Okay, that's from the slope equation we have got.
Right. Okay, so both the values alpha and k are equal to 5. Okay,
Okay.
Yeah, yes.
you just go through the question once again. Okay,
Yeah, sure.
so I prepared more questions for you. Like now, there are many more questions which we can do from this topic. But anyways, we were engaged in pretty good conversations